Hello everyone, I'm Anasabe from Japan. This research is joint work with NEC and the University of Tokyo. The presentation title is Data Diet Pills in Network Video Quality Control System for Traffic Usage Reduction. At first, have you ever faced an uphill battle to make ends meet at the end of the month due to forgetful extravagant spending earlier? In this case, it would be helpful to have the choice to get advice from financial advisors about balancing your money by consumption saving. This scenario is analogous to video streaming services over the internet. Stakeholders might need to degrade video resolution relative to the best effort quality. In the first case, mobile subscribers are commonly billed according to their data usage. Best effort quality video is a good experience for users, but they consume a lot of data volume. Therefore, subscribers often struggle to avoid going over their data limit. In the second case, video traffic increases due to people staying at home because of the COVID-19 pandemic. The increased traffic incurs congestion on the internet. So video traffic reduction is required to avoid such congestion. In such cases, subscribers and OTT providers can control video quality on their own. But there is a trade-off between obtaining the benefits of traffic reduction and conducting cumbersome tasks. So we'll try to reduce traffic usage in the video delivery chain to provide unattended data diet services for end users and OTT providers. HTTP adaptive streaming is widely used in video streaming services on the internet, and it can be roughly categorized into server-based, network-assisted, and client-based approaches. Server and client-side approaches have the advantage of accurate video quality control, but traffic usage is unknown. On the other hand, network-side approaches have the advantage of knowing the traffic usage of users and OTT providers. So because network-assisted adaptation is suitable for our scenarios, we address the traffic reduction challenge from a network operator perspective. Conventional studies on network-assisted adaptation focus on the throughput fairness between clients and applications. Moreover, the control target is non-encrypted traffic. On the other hand, our study addresses the challenge of reducing mobile data consumption while preserving video streaming quality via encrypted traffic. The most straightforward approach to control video quality on a network device is to shape throughput at a certain rate. Constant rate shaping can avoid complex operations, but we are concerned here with excessive video quality degradation. That is, the throughput of certain applications must always be constant regardless of their network condition. In the worst case, such operations to degrade video quality excessively may result in customer dissatisfaction. So adaptive rate shaping is required. Because video streaming quality depends on achievable throughput, Excessive quality degradation can be mitigated by changing the shaping rate depending on the initial video quality when the user starts watching. We call this relative pacing. In the relative pacing, video quality needs to be identified quickly and accurately from encrypted traffic. This is a second challenge. Note that our method is discussed mainly for YouTube traffic because of its popularity, technique, and easy to collect labeled data. To address two challenges of adaptive rate shaping and timely video quality identification, we propose NetPacer. NetPacer detects the initial burst phase from observed traffic and estimates the initial bitrate. After estimating bitrate, NetPacer decides a shaping rate for degrading video quality by one level relative to the initial video quality. Finally, playback resolution degrades by one level. The following pages show how these functions work. In the initial burst detection function, NetPacer extracts communicated IP packets during the initial burst phase to identify video quality in real time. In YouTube AVR streaming, there are two transmission phases of the initial burst and throttling phase. The video client transmits multiple chunk requests to fill their buffer as quickly as possible in the IV phase. So we identify packets in the IV phase by finding a larger packet interval than a threshold. In our study, 2 seconds is the optimal value for the threshold. Next, we face the challenge of identifying the initial bitrate from packets in the initial burst phase. Generally, the bitrate can be calculated by video size divided by video length. So we calculate the estimated bitrate by this equation as a heuristic approach. This approach is easy to implement, but has a shortcoming to be sensitive to communication quality changes. To resolve this, we propose an approach based on machine learning. The ML-based approach uses IP packet level statistics. We evaluate the bitrate estimation accuracy for these two approaches for 1018 videos. The ML-based approach reduces the MAE by 0.27 points and the heuristic approach, so we use the ML-based approach for the bitrate identifier in NetPacer. Our final challenge is deciding the shaping rate for relative pacing. Images are composed of multiple pixels, so higher resolution videos are composed of a larger number of pixels. So when the estimated bitrate is given, the bitrate to degrade by one level becomes the shaping rate. However, there are inconsistencies between this equation and the actual bitrate due to media compression, which may cause shaping rate error. We then propose a statistical approach for accurate shaping rate calculation. Our statistical approach is based on the idea that the lower probability of each video in CDF tends to be constant regardless of resolution. For example, consider one video to capture moving objects. Even if the video is encoded with lower resolution or higher resolution, we intuitively know that the bitrate of the video is larger than that of videos capturing static scenes. We compare errors of shaping rate, and the results show the statistical approach is more accurate than the heuristic approach. In our evaluation, we watch YouTube videos on a smartphone connected to the internet via Wi-Fi router. To observe and control YouTube traffic, an L2 switch connects the Wi-Fi router, the internet, and a PC with NetPacer. The switch forwards packets corresponding to the smartphone to NetPacer. As for performance measures, we evaluate the traffic reduction ratio and the QoE degradation. We first show the results of the traffic reduction effect by NetPacer. In watching a video without NetPacer, the resolution does not change from the start of watching to the end. In contrast, when we run NetPacer, the resolution degrades from the initial resolution by one level as we intended for all access patterns. Therefore, the download data size is reduced in the case of running NetPacer. From a statistical view, we evaluate the performance of NetPacer for 50 videos. The results show that NetPacer reduces traffic volume for almost all videos and keeps the QoE degradation from 0.23 to 0.43 points on average. Therefore, NetPacer is effective to degrade traffic usage but less QoE degradation. We have a lot of future work. For example, robustness in different networks, availability for other streaming services, and conflicts with video streaming applications. Let me conclude this presentation. We want to realize the traffic usage reduction in the video delivery chain for providing attended data diet services for users and OTT providers. Our contributions are as follows. First, we define two technical challenges for the in-network video traffic shaping. Second, we develop NetPacer to solve the two challenges. Third, we demonstrate NetPacer can degrade traffic usage for 50 videos in our lab environment. That's all. Thank you for your attention.